Yeah.
I'll do some introduction. If there is it's Where do you want to start? You want to show?
Thanks everyone for coming. We're very happy to have Gabriel Greene-Diniz from Quantinuum today. And maybe first we can begin with a round of introductions so we get to know everyone. So I'm Linda. I'm a second year PhD student in Alex's group, and I work on quantum computing methods for chemistry.
Hi, I'm Sarah. I'm a fourth PhD student in Alex's group, and I also work on quantum computing algorithms chemistry.
Me, David, and quantum chemistry at Quantinuum. I mean, computing. Yeah.
I'm Max. I'm doing a part 2 actually, but I met Lila in the showcase day, and I got interested. So nice to meet you all.
Welcome.
Hi, I'm Ollie. I'm doing my PhD in the maths department, working on a mixture of fundamental cubic mapping schemes and quantum metropolis and related ideas.
Hi, I'm Alex Dom. I'm a PI in chemistry, and I do all sorts of quantum chemistry algorithms and quantum algorithms and all sorts of things like that.
Hi, I'm Benzer. I'm a first year PhD. I'm currently working on power-induced big selectivity effect, but I did my master's project on quantum.
So I'm Choi. I'm a second year PhD student in David Wilson's group, and I'm focusing on the energy landscape of variational quantum algorithms.
Hi, I'm Yusuf. I'm a third year student in real estate as well, and I look at different kinds of energy landscapes.
And hello, everyone. My name is Gabriel. I'm a senior research scientist working under David in Quantinuum in the quantum chemistry group there. And so I work on various different quantum algorithms for chemistry and a little bit of condensed matter physics too. And so what I'll do today is I'll showcase, I suppose, some of the methods I've been working on. In particular, I'm going to talk about one way that we do chemical state preparation in InQuanto, which is to basically it's a code that allows you to linearly combine Slater determinants or octopation number configurations on the quantum circuit. So you can kind of design a quantum circuit to do selected CI in a sense. You can think of it that way, or another way to think of it is that you have it's a method to generate a quantum circuit that does multi-reference state preparation. Kind of in a convenient way that's we think can be in many situations more convenient than usual VQE ancestors or something. And the other part I'll talk about is quantum subspace methods, and these two things kind of can be combined together because many quantum subspace methods like a good initial state preparation. And the chemical state preparation I'm going to talk about as well kind of feeds into that in a nice way. So the subspace methods we're using to get good approximations to the ground state energy that do not need to VQE or the kind of some of the difficulties associated with VQE, like complicated landscapes and having barren plateaus and getting stuck in local minima and stuff. And also on the kind of scalability side, VQE has a problem with a large number of measurements in general. So subspace methods were introduced as a way to kind of bypass some of these issues and get a good ground state energy approximation. So as I'll show later, they do well when you have a good way to prepare an approximate but cheap approximation to the ground state. So subspace methods generally they solve a projection of the Schrodinger equation onto some subspace spanned by these vectors v. And the particular one we're going to talk about is the Krylov subspace method, where the v's are generated by applications of powers of the Hamiltonian to some reference state. So I'll show you how that can be used to measure a good approximation to the energy on a quantum circuit, And I'll also show how you can use a similar subspace method to do beyond ground state properties. In particular, I'm going to show you how you can build a Green's function out of it. So that involves excited states and some dynamical properties. So ground state energy and beyond ground state properties can be kind of gained by quantum subspace methods, which in turn work well by having a good initial state preparation method. So so this slide probably not necessary for this crowd, but just for completeness, so in ab initio quantum chemistry, generally we want to express the ground state as in terms of excitations on some reference on the Hartree-Fock solution, such that the ground state can be expressed as some linear combination of reference and excited state configurations. And that's the kind of thing explicitly we can prepare on a quantum circuit using the method I'll talk about, which involves Gibbons rotations. To kind of introduce how to use Gibbons rotations to prepare linear combinations of these ON occupation number configurations. As we well know, so excitations in chemistry map. You can think of them as a map between particle conserving configurations. So if you start with some Hartree-Fock configuration, you're going to map that to some normalized linear combination between that one and some other excited one. Where in this case here, it's just an example using a single excitation. So the electron has moved from one spin orbital to another. You can encode that using unitary matrices like the following, which actually rotate the initial reference state in a two-dimensional subspace of a regular space, and that is so the two dimensions there you're talking about are dimensions kind of defined by these two state determinants, and you're kind of rotating in that two-dimensional plane by applying this Gibbons rotations, where the different angles of that rotation are encoded by the mixing coefficients. So these A, B, C, and D's here will be related to these state determinant coefficients in your wave function, and you can get that kind of excitation mapping, if you will, from Gibbons rotation. And that's useful in quantum circuits because, as I'll show you, there are explicit quantum circuit constructions for these Gibbons rotations that can preserve particle number and other symmetries that you're interested in chemistry. And for that reason, Arachola et al. From Xanadu proved that actually these Gibbons rotations are universal for quantum chemistry. Universal in the sense that all particle number, all in general symmetry conserving wave functions can be generated by applications of a Gibbons rotation to some reference. So, and then because these Gibbons rotations are encodable by a quantum circuit, that means that Gibbons rotations provide a universal way to do chemistry on the quantum circuit. That was the basics of that paper. And so what we did was we took that paper and used their and read their proofs, took their proofs, and then kind of converted them into working code that InQuanto uses to build these multi-reference states or CI. So as I said, the applications for this kind of thing are multi-reference state preparation. You can also make these coefficients variational parameters, and therefore, yes, you can do something like variational configuration interaction on the quantum circuit if that quantum circuit was then an ansatz for VQE. In this particular talk, I'm going to focus more on just this multi-reference state preparation application of it, which is kind of the same method, but now the coefficients are fixed to something you select in advance. So kind of this slide kind of shows is very, very basic example showing kind of how or why Gibbons rotations are particle conserving. So we work in the Jordan-Wigner for this talk here. I'm going to assume the Jordan-Wigner encoding, where indexes of the qubits correspond to spin orbitals, and the 0 or 1 value corresponds to whether that spin orbital is occupied or not. So in the computational basis, so expressing that Gibbons rotation unitary matrix in the computational basis, you can then think of what's this going to do to some state vector that you apply it to. So this equation here is very schematic. In general, there should be normalized coefficients here. I'm leaving them out just for kind of brevity. but schematically, basically, you have some state vector and you apply this Gibbons rotation unitary to it. Well, what happens is the result kind of shows you how and why Gibbons rotations are kind of particle conserving, because they will only mix basis states in the state vector that have the same number of particles. So the whole state vector is kind of spanned by all of these basis states. So that means that it can't really mix this with any other one, because all the other ones have different numbers of particles. And similarly for the 1,1, it can't mix that with anything because all of those have the same number of particles. So the only basis states it can mix are these two. And that means, and that's the result of its kind of matrix structure, and or intuitively that means that Gibbons rotations will preserve the particle number of the basis state that you apply it to. There's a big caveat there though, because that assumes that, what I said there about its symmetry conservation is specific to it being applied to one single reference state. When that Gibbons rotation is applied to a more complicated circuit, which itself already contains many basis states, other things need to be applied to this Gibbons rotation unitary. In particular, it needs to be controlled on other qubits. And so actually the algorithm we developed was, the whole difficulty behind it was, it's all right. The main difficulty behind that algorithm was actually figuring out how and when to apply these controls in a kind of smart way, and that also doesn't lead to too much overhead than what is necessary.
Yeah, can I ask you that?
Yeah, please, yeah.
So to keep it particle number preserving, you just need to make sure your Gibbons rotations are between effectively determinants with the same number of particles.
That's right.
But to do symmetry preservation, that's more complicated.
That's more complicated, yes, but because of it, you're completely right. But because of how, so this slide is not really good for explaining for kind of backing up what I'm going to say here now. But basically, because of how the code works, it will only linearly combine the determinants that you select at the beginning. So if as the user you select determinants that themselves are spin conserving, and then you apply the Gibbons rotations to the appropriate reference, the resulting state vector must have the same symmetry as what you plugged in to the determinants that you're inputting. So it's kind of comes out of how the code works and how it kind of comes out of how the code works. But you're kind of right, Alex, in that again, like a single Gibbons rotation, the symmetry it preserves depends on the matrix elements and what basis states it's going to mix. But the basis states it's going to mix is kind of a function of what the user gave it in the beginning, and it won't. It might be more clear in the next slide when I actually do an example. But you'll see that it won't actually mix in any other basis states other than the ones you select. So if the ones you select are spin conserving, the whole thing will be the circuit will be spin conserving in the end. Yes. Oh yeah, and this slide is just to say that, so all those examples I mentioned there are for single excitations. So where you're just exciting a single electron from your spin orbital. This is of course perfectly applicable to other n-body in general excitations. You can do doubles, and you can do excitations in general of any order. There are Gibbons constructions for and this is just to say that so each of those so each of these are kind of U2 transformations, and they will so they'll commute with the particle number operator.
And so the particle number conservation that you said also works for more than 2 qubits, right?
Yeah, it does. Absolutely, it does. Yeah. So those examples were really just simple, just so I can put them on a slide. But absolutely, it all applies to these general excitations. So there are from the so that our Scholle paper I mentioned cited another paper by Anselmetti who worked out explicit Gibbons rotation gate constructions for the particle conserving Gibbons rotations. And what that means for us is that there are Gibbons rotations for single excitations and double excitations that do not scale with the number of qubits. What I mean by that is, so double excitation is applied to 4 qubits, but if this is part of if this is part of the state that consists of many more qubits, the depth of this will not scale with those extra qubits. It's similar to the single excitation. However, when you have to go to greater than doubles excitations, then the depth does scale with respect to the number of qubits, because those greater than double excitations are built by a series of controlled swaps followed by a multi-controlled version of this single excitation. So this G1 gate is kind of used as a primitive to build up the entire Gibbons rotation unitary for greater than double excitations. But because of that construction, that means that greater than doubles are expensive and their depth scales with the number of qubits, unlike these two. So if you have a state vector that in which all of the determinants are separated by the first by at most the doubles excitation, you're kind of doing well, because the circuit you'll end up there will be relatively cheap. So
Is there a limit on what you can describe with just doubles? If that makes sense. I mean, I can't.
well, you can go into things like those paired double ansatz, and you can think about different ansatz schemes like that. But you're certainly not restricted to doubles in this. It's just not restricted in principle. It's just kind of more a cost thing. In case it's not clear, this double is a general doubles. It doesn't necessarily mean so this this is a pair of doubles, but it doesn't have to be paired. It can be any kind of doubles. Excitation will be can be built from a circuit like.
So in this bottom one, are you that's a specific Gibbons rotation between two Slater determinants, effectively, rather which just happen to be doubles.
Yeah.
And the representation is next to each other. That's why it's sort of close, effectively. So if you wanted to do very general ones, as you say, you basically swap everything until you get to things next to each other, do the Gibbons rotation, then swap back.
That's right. Yeah. To do the greater than doubles. Yeah. Let me do a small detour. I'll show you. I left it to the supplementary, but yeah, since it's a good thing to raise, I suppose. And this one here. So this would be a triple excitation. So this G box here is the G1 we showed, the G1 I showed earlier. So what's happening here is you start off with so on this side of the circuit, you're going to have this reference state. And what you do with the swaps, basically, so you're going to have a series of swaps that swap the zeros and ones of your reference until the swapped reference is one body excitation away from the target reference. Then you apply the one body excitation and then you unswap back. So that's how you can do triples in that case, and you can and with more swaps and everything you can do greater than you can do any excitation. But because of these multi-controls you see, so these multi-controls you span all the qubits on your circuit, and then when you decompose those multi-controls into an actual gate set, that means that the unlike the fixed construction for single and doubles, greater than double circuits will scale with the number of qubits in the whole state.
And I think maybe that was the same question of Alex, but how is the antisymmetry delay function observed here? Is it?
Well, so here's the thing. You don't actually, for example, in UCC, you need to provide, when you have an excitation between spin orbitals that are kind of far apart, you need to provide these, you need to keep track of the -1 factor. And that's done in UCC by when you Jordan-Wigner fermionic operators to qubit operators, you have these string of Zs to keep track of this -1 factor. Here, what we're doing is directly mixing a reference state at the beginning, which is just the bit string, to other bit strings. So that is not actually a problem here. You can just apply the Gibbons unitary directly to it, and it will mix the two determinants by whatever coefficients you select here.
Okay.
So it's not really unlike there is in UCC where you have the Jordan-Wigner transform fermionic operators. We're not Jordan-Wigner transforming fermionic. We're starting directly from kind of qubit operations, and then just seeing what operations we need to do to mix bit strings in a way that can serve the Hamming weight, really, because we're in Jordan-Wigner. So we need qubit operations that preserve the number of ones between the bit strings, and do not mix in any other unwanted bit strings. Once you satisfy those, you kind of get the actual fermionic wave function representation directly without these Z strings. So it does have there's an advantage there, and there's an obvious advantage there too for this over a general doubles in UCC, because in UCC that would have extra Z strings to keep track of it.
Yeah.
But here we don't, because we're kind of directly operating in qubit space if that makes sense. Yeah, and this slide gets a bit complicated, but the point here is that a really nice feature of this, which is a little harder to do with other ansatses, is that if you were using this kind of approach to do a variational ansatz like in BQE, well, the variational parameters theta are directly related to the Slater determinant coefficients in a way that is kind of very convenient, because once you have the VQE parameters, you can work out the state vector coefficient, the actual coefficients of the Slater determinant, without explicitly diagonalizing the quantum circuit. So you can very kind of conveniently relate angles of the gates on the circuit to fermionic chemistry information, which is the coefficients of the Slater determinants, kind of directly. You have this direct relation, and so you know what gate is corresponding to what correlation and what excitation, which is, it's not impossible for UCC, but it's a little more inconvenient with other variation of ansatzes. And how that's done is through the series of kind of a sequence of operations. So what we have here, so let's say we want to mix these basis states outside, and each of them have a coefficient CI. The first thing you consider is, okay, so imagine we knew what the Gibbons rotations we need to do this. So you consider the building up the whole linear combination kind of one by one, like in a sequence. So starting from x1, you need a Gibbons rotation to map. You map x1 to a linear combination of x1 and x2, and each of the linear combinations always has to be normalized. So that means that you pick one of the given coefficients. You can think of them as user selected coefficients that the user wants to, for which the user wants to linearly combine these determinants. You pick one of them, and then you'll get the other one by normalization with the one you've picked. So in this case we picked C2. And now we're going to end up with a normalized linear combination. We need something that is normalized relative to C2. So that I'm going to call that alpha there. And then you consider the next sequence of rotations, which kind of conceptually is like mixing. You need a Gibbons rotation to mix x1 with x3. But because x1 was mapped to x1 and x2, you're actually mapping x1 and x2 to x1, x2, x3. Again, by remultiplying back the normalizations for the coefficients, such that the whole linear combination remains normalized, and you continue that sequence up to all of the xi's that you want. And what you get in the end is that these alphas that you worked out from normalizations are directly related back to the coefficients that the user chose in the beginning. And what that means in turn is just what I said earlier, is that so these alphas are related to the angles in the Gibbons rotations by inverse cosine functions. So the theta there is going to be related to the arc cos. The alpha here is going to be related to the arc cos of the ice Gibbons rotation, and the arc cos of the theta of the ice Gibbons rotation, and that theta will be a variational parameter in your VQE. And that's what I mean when I say that the VQE variational parameters for which are rotation angles for gates on the quantum circuit can be directly related back to the basically the CI coefficients of your CI expansion of your wave function. And that's kind of a very useful thing because you know explicitly where in your circuit there is particular kinds of correlation. So you know what gates are contributing to what correlation relative to the Hartree-Fock reference. That makes sense. But that's kind of a nice feature of this for analyzing methods and analyzing states and molecules and stuff. Yeah, it's kind of useful for that.
And how scalable is that approach?
that's the dirty secret, which is that this scales as badly as FCI. Because, to represent the exact state, because you're going to have a Gibbons rotation for every FCI basis state. But the point is that we don't want to, especially for the subspace methods I'm going to mention later, we don't want to prepare the exact ground state. We want to prepare a smart approximation to the ground state from which a subspace method can use to then generate a better approximation, for example, to the energy. And so this is very convenient for linear combining small numbers of configurations to generate these slightly better than Hartree-Fock wave functions from which a subspace method that can improve much more.
Yeah.
And you can do a similar thing with UCC again, but again, it's kind of inconvenient because you have this unitary that is an excitation represented by an exponential excitation operators, and you can do some math to work out exactly what those determinants are, or you can just run this code and you know exactly what the determinants are from the beginning. So it's kind of convenient that way. But yeah, to get the exact state, not good, not good in general.
If we had a very, very large number of qubits, but we're only caring about, a small subset, let's say we're doing matrix space or something in our initial preparation, you need to control on it, if you knew the initial states of a whole load of the frozen orbitals, you wouldn't need to control on them, but if you had done anything on them, you'd have to control on them so you don't select determinants where you've done something in that. So the Gibbons rotations end up being controlled by everything outside the space you care about, and that's a lot of controls.
That is what you're saying there is what I'm going to call in the next slide the naive approach.
Okay, yeah.
Because yes, in general, yeah, you would naively think, and that's exactly what I did when I first started to implement this, which is that, yeah, it looks like so you would just need to control every Gibbons rotation on every other qubit that it's not applied to. But there are some rules and heuristics you can use to actually reduce those number of qubits. And actually, in many cases, there are Gibbons rotations that don't need any controls at all. Because, as I'll show you in the next slide, because you can end up in a case where a Gibbons rotation applied at an arbitrary point in the circuit cannot act on any of the basis states already there. Again, the reason for that goes back again to that matrix representation, because of its matrix elements, it won't mix any other basis states other than the one that it wants. There are situations where it will, and then you have to control, but there are times when it won't, and figuring out that when to need them or not was the kind of difficulty in implementing this in the first place. So you can get away with easier than having to control on everything in many cases. So the example of that I'll show here. So let's say we want to prepare this kind of state, and this comes from that Arashola paper. It comes from that paper. So let's say this is our Hartree-Fock reference. So because of the, as I mentioned earlier, you have a sequence of rotations, you apply one at a time. So we're going to apply the first Gibbons rotation, which will mix, let's call it X1 with X2. So we're going to mix the two of these in the first Gibbons rotation. And that will be this box here. So you start off with this reference and you apply this Gibbons rotation to it, and then at this point in the circuit, you will linearly combine the two of these to within some normalized coefficients, but we'll ignore normalization coefficients for now. Just at this point, you can consider that you have these two determinants. And by definition, the first Gibbons rotation applied to the sequence never needs controls by definition. The next one then, so we apply every Gibbons rotation we use, we apply it kind of relative to the first, and then control it as necessary in order to achieve only the determinants that we want. So for the mix in the third determinant, we're going to consider mixing this with this. So that means we need a double excitation from here to here, and then that's what this is. So this kind of decompose or delocalized G2, it just means that it's a Gibbons rotation G2 box applied now to these 4 qubits rather than these. It's just a 4 qubit, another 4 qubit a gate. And now naively, because it's not the first, and there's kind of the possibility of other basis states there already, naively we would think, okay, then we have to control all the other qubits to be in the state that that we want it to be in order to mix the correct determinant with this. So that means naively we would think we would have to control this G2 box on these two qubits being 0. And you can do that, and then at that point you'll have these three determinants. And then for the same reasons, then you then have a single excitation Gibbons rotation controlled on this qubit being 1, such that then at this point you have the desired linear combination of determinants. And that with the error back-end gate set gave me that number of gates and that depth. But you can be a little smarter about it, because you can realize that actually in this case, this Gibbons rotation, which will have a matrix representation that will mix these qubit modes, it won't be possible for it to mix to mix in this one too, because it can't do anything to that basis state. If you, I'm not doing it here, but if you expanded out the matrix representation of this G2, you would see that actually for this, and then apply that matrix representation to a big 6-qubit state vector, you would see that that matrix doesn't do anything to this. It only mixes these two. And that means that in this particular case, you actually don't need these controls here. So, or in general, you could say that controls are only needed on a Gibbons rotation if there is a basis state there already that is rotatable by that G. And there isn't any other basis state rotatable by that G other than the one that we want to mix with already. So that means that in that case, actually, you don't need any controls for it. And then, but however, for the next one, because it's applied at this point, you do need controls for it, because this could, so this one, you want to mix this and this. So that means an excitation from here to here. But actually, if you look at it, this one also has a 0 and 1 in the same qubit nodes. So this G1 could also mix this one too, unless you had the control here that says only apply this G1 when this qubit is in state 1. Mm-hmm. And therefore, at this point, then you have the exact same state vector with a vastly reduced number of gates and depth. So you can really reduce that depth due to the controls by being smart about where to apply the controls. And so that was the difficulty. I mean, I can go into more detail about the algorithm, but it gets very complicated. I have a slide in the supplementary.
So the sparser this is, the nicer it becomes, but the more overlap there is between the bit strings of your different determinants you want to put there, the harder it becomes, because effectively you need to start multiply controlling, having put extra parameters in. So is there a
when you say that there's more overlap, are you saying that the use of controls depends on these coefficients?
Oh no, as in depends on precisely the bit strings. So the fact that you could do that control or not put the control on the second one is because there was no bit string overlap between
those two determinants. Yeah.
So and if you've got a sparse waveforms you want to make, then that's unlikely to be the case.
Mm-hmm.
But is there a relationship, maybe when you develop this, between the number of gates you need and things like that, and the sparse, how much the sparse data wave you're going to make?
In this one, basically, you're kind of it depends on a lot of things. Whether the less than exact wave function, how many determinants you have in it, and how much they're separated. There's another algorithm. I wasn't going to talk about this because I haven't implemented it yet. It's still it's in the middle of being implemented. But there is a whole other technique to do this called sparse quantum state preparation, in which which it can be shown that it actually scales linearly if your wave function satisfies a certain sparsity condition. What that sparsity condition is that if the number of basis states in it scales less than or equal to the dimensionality, the full dimensionality, which is 2 to the n, divided by n. So if the number of basis states scales less than that factor, that algorithm, not this one, that algorithm I'm working on does actually have will be linearly scaled. And that for kind of the same reasons as this, but even more so. That other algorithm is super useful for as an initial state preparation for subspace methods. Also could be for quantum phase estimation, or anything in which you want a reasonable approximation to the ground state that's not too expensive, but also leaves room for the other unitaries of the quantum algorithm to improve on it. So quantum subspace, quantum phase estimation, that kind of thing. And if you've read papers by Garnet Chan, who very, very justifiably kind of complains that, look, these methods they might have a big problem, which is that you need a good state in the first place, but that state preparation could scale very badly, even exponentially. So that kind of kills your quantum advantage. Well, now if you have a sparse state preparation to prepare states that are not the exact state, but good enough for another algorithm to use, and that sparse state preparator is linearly scaling, then you're kind of, that's good, right? Because you don't have an expensive one anymore.
So
Expensive. Sorry.
Is there any improvement in this, like provable improvement compared to naive state preparation? As in, like, in this particular case, you might be better off with naive state preparation, but as it gets more complicated.
By naive state preparation, what you
Just like doing rotations onto just doing control rotations onto another answer that are in there. Better.
Well, I guess you can do that, but I think really the point of this is that you're not looking to get like a really good representation of the ground state. You're kind of looking for a cheap way to do a little better than Hartree-Fock, such that another algorithm can improve on it. Improve on it for some property you actually want to measure, like the energy or something like that. But if you're talking about, so that naive state preparation will also scale exponentially.
Yeah, so if you had all of your basis states, then it would be exponentially costly.
But then you would have the exact ground state.
Yeah, exactly. But if you're operating on some reduced sparse condition, then it would work well. But what's the regime in which the Gibbons rotations are like outperform the just doing a naive approach?
It's a good question. Hard to say, to be honest. It depends.
And they should be
gonna depend on-
they're all just rotation gates as well.
Sorry.
They should be completely because they're all just rotation gates.
Sure.
You should be able to do it well with these rotations.
You might be able to do it badly, but the best case, you can probably do it equally well, I'd imagine.
Yeah.
So, but finding that might be the hard bit.
Yes.
Actually,
Definitely.
You're finding the efficient state preparation.
Absolutely. But I keep kind of efficient state preparation, as far as I understand, usually kind of tries to find the most efficient way to generate the exact state, or as close as possible to the exact state. And in principle, this can do this if you just have enough Gibbons rotation layers. But practically speaking, this isn't really a way to prepare the exact state. It's just a way to do some approximation to some good enough approximation that will give you an overlap with your true ground state better than the overlap you would get with the Hartree-Fock state. And as I'll show later, that's not just a convenience thing, but when you're looking at like strongly correlated molecules in transition states and stuff, actually you need something slightly better than the Hartree-Fock state. Even if you have a quantum algorithm that will introduce correlation later on for the energy, it's still the example I'll show later. It still can't do good if you only had the Hartree-Fock state. However, if you only had like two determinants, which is only a small kind of overhead of number of gates, you could then that quantum algorithm can do much better because it has more to kind of work on in the initial state than the Hartree-Fock. Yeah. So if you want to just prepare a state with a little bit more correlation than the Hartree-Fock, this can be very, very convenient because you can very selectively, select exactly which determinant the Hartree-Fock is mixing with. Let's see. Yes, so this is the use case for the quantum subspace approach to get the energy. So we're looking at this beryllium insertion into H2, which is a kind of it's kind of a prototypical example for strong correlation. It goes back to the 80s. At this kind of midpoint of the reaction here, the system becomes very strongly multi-reference, and things like Hartree-Fock start to, so this here is the overlap with the of the exact state with the Hartree-Fock, and I think the red is a multi-reference generalized UCC that the authors did, which is very, very, very expensive. And yeah, so you can see it there in the overlap of the wave function. You can see the strong correlated nature in the energy error you get between Hartree-Fock and the exact state. And yeah, so its energy landscape here kind of, you see that that's kind of what would be called the quasi-degenerate point as the potential energy surfaces start to meet. Yeah, so before I show you the results of the Gibbons rotation, I'll take a small detour into quantum subspace theory. So as I said, it's a way to improve to get a good estimate of the ground state energy, and people have shown that it can be more robust to noise than VQE. It's related to so this method here called QCM4 stands for quantum computed moments to the fourth order, and it's essentially a variant of a quantum subspace expansion involving the Krylov subspace. And the 4 there means that, so as I said, the Krylov subspace is generated by applications of power of the Hamiltonian to some reference. And the 4 means that you cap that at the 4th power of the Hamiltonian, because people have derived an analytic relation of the energy to the 4th order of the Hamiltonian through things called cumulants or connected moments. And these connected moments provide the reason for them. You have to kind of go deep into the theory, because these quantum computed this moment expansion of the Krylov space was derived because you want to generate thermodynamic estimates of the energy for extensive systems. And that means that, but there was a problem there because because you have powers of the Hamiltonian involved in your energy. That means that the volume dependence then doesn't have the same volume dependence of the straightforward expectation value. And that means that getting the energy kind of directly from moments is problematic. But so Lloyd Hollenberg and et al. Derived these cumulants that are functions of the Hamiltonians, and these cumulants scale the same way as the expectation value. So for extensive systems, that was very useful because it meant that the energy estimate from the cumulants was still kind of thermodynamically viable, if you will, that there was a limit of the energy estimate in the limit of volume going towards infinity that actually existed. So that provided them kind of an analytic approximation to the energy, and then further kind of derivations led them to this expression for the energy. So typically what you have is, I'll show this later in another context, is that you use these cumulants to build up the Lanczos coefficients for an orthonormal Krylov basis. And from those Lanczos coefficients, you can build up the tridiagonal representation of the Hamiltonian, which is much easier to solve than your original Hamiltonian. Then getting the lowest eigenvalue of that tridiagonal Hamiltonian would give you the energy estimate for that quantum computed moments application. However, you can skip that eigensolution of the tridiagonal Hamiltonian entirely via this analytic form of the energy, where what you do is at the quantum circuit is, so you have your state prep, and that's where the Gibbons rotations will be. Then you apply your moments of the Hamiltonian, and we do this in a Pauli operator averaging fashion, so that actually there's going to be kind of a circuit for every Pauli term in the Hamiltonian, and in particular for every Pauli term in the powers of the Hamiltonian. And then you're going to measure those terms to get the expectation values of the powers of the Hamiltonian, and then from those measurements, you plug those into a classical, just classically plug them into this expression here, and then from that you generate your cumulants according to that power, and then from the cumulants up to the 4th power, you then plug them into this formula, and you get the usually pretty good approximation to the energy. Which is, and very importantly, that approximation to the energy is much better than the energy represented by the input state. So by that I mean, if you just took this input state and got its expectation with respect to the Hamiltonian, you would get a certain energy. However, if you took that input state and then plugged it into this involving powers of the Hamiltonian, you get this energy, which is much better than the expectation of the Hamiltonian with respect to the state. So by plugging in a cheap version of a very, very cheap and maybe far from exact approximation to the ground state, and then measuring these moments at a Hamiltonian, you can get an energy that is much better than the energy represented by your input state in the first place. So that's why I was kind of trying to justify that using Gibbons rotations to generate a very cheap approximation, but only slightly better than Hartree-Fock. You can then use that to get a much better approximation to the energy than what you would have just with the initial state.
So are you just preparing a state and then taking Pauli measurements of the state?
Basically, yes. Yeah.
What's the quantum advantage to that? Whereas if I know what state I'm going to prepare, and I know what Pauli measurements I'm going to take, I can do that on like a normal computer. No.
Well, you can because kind of storing the wave function on the classical computer is in general hard.
Oh, I see. Okay,
Yeah.
so we might be preparing a state that we couldn't write down. For.
Oh yeah, I see.
Since we derived the state originally from this.
Well, so that's the state you did in your state prep, but every time you apply the Hamiltonian in your state.
You get a better energy than that state, right?
Yes. Okay, I see. Yeah.
And the fourth part of the Hamiltonian creates a lot of stuff.
But the fourth part of the Hamiltonian, we're just measuring Pauli terms of, say, like a certain body. So if we do classical shadows, that's probably the most efficient way of measuring them.
I'm not sure about that. But remember, so you will have, you kind of, in principle, or kind of naively, if you just multiply the Pauli representation of the Hamiltonian by itself, you end up with what looks like many terms. But many of these terms commute with each other. So the number of circuits you have to measure can be much less than the number of terms you would have by just straightforwardly multiplying the Hamiltonian.
Okay.
So that gives you kind of, so you end up with a number of circuits to measure far less than the number of Pauli terms you kind of you have. So there's there's some kind of utility of it there because you had a cheap state, then you have a cheaper state, and then you have this kind of quantum method to measure the terms of the Hamiltonian. Is there any other comments there?
So just to be sure, in that you never diagonalize anything, like you never even detract the diagonal of the turn.
No,
Yeah.
he's not doing that. That's a good point. You just have your moments, and then you generate the cumulants from them, and then from that so this is the application of those methods to that BH2 use case. So this top graph here is just showing that so the blue line is the Hartree-Fock reference, and we're just showing how the weight of that Hartree-Fock reference changes as a function of the reaction path, and the strongly correlated point, the transition point, was this point E here. So that's the point where the Hartree-Fock has the least weight, and there's another determinant that's coming up having almost equal weight, so that's kind of very typical of a strongly correlated state. And this result here is kind of shows what I was saying. So the first, second, third, fourth, these correspond to QCM4, in which first means Hartree-Fock was the input state, second means these two, which one? So it's going to be these two determinants. So it's the Hartree-Fock mixed with the next weighted, largely weighted determinants, and then three determinants and four. So Hartree-Fock itself doesn't give a good energy at all. So the energy benchmark I'm using is the CAS-SCF for the 8 spin orbital active space. Hartree-Fock doesn't do great. CCSD with a single reference doesn't do great either. It kind of it's missing a lot of the correlation there. But now, if you apply QCM4 with just one Hartree-Fock, it does actually better than CCSD, but still kind of significantly off the benchmark. But now, if you just give QCM4 one more determinant, you already get the full CAS-CF energy in that space. where the CAS-SDF energy classically had some 12 determinants or something inside the code that it was linearly combining. So classically, we kind of needed 12 determinants there to do that energy. But through the QCM method, we can get the same energy with just kind of 2 determinants plus measuring all the moments.
So to find that linear combination of those 2 determinants, you just do a 2 determinant CI and work out the coefficients, or are you more permanent than that?
You can pick,
Because you could get it wrong.
that's right, but because we've done, yeah, so you can, yeah, absolutely. So you can, in this case, we just picked the coefficients from the CAS-SDF for those 2 determinants, and then just renormalize it, just renormalize it. So again, QCM4, it just needs some approximation to the ground state, and it can do well, even if those coefficients are not exactly the coefficients it would have in the CAS-SDF. So going on to another application of the quantum subspace stuff. Moving into a different kind of area now of Green's functions. So these are things that are important for kind of dynamical electronic responses. You can get things like photo emission, photo absorption, conductivity too from them. And mathematically, they're used to solve ordinary differential equations. Where if you had this linear operator that had eigenstates and you knew what they were, you could directly build a Green's function and then use that to solve ordinary differential equations like that. For chemistry, yeah, so they're very useful for getting spectral properties of your system. And the exact kind of Leibniz representation of this looks like this. So you split up into these particle and hole excitations. But you can use the subspace method I mentioned earlier, involving these moments. To build the orthonormal Lanchas spaces, and this is this will be the tridiagonal matrix I mentioned earlier. But in this case, what we can do is build up something like a tridiagonal, the coefficients of the tridiagonal matrix. You can build those from measurements of the moments that I'll show later. In that case, the operator won't be explicitly the Hamiltonian, but it will be what I call a sandwiched Hamiltonian, sandwiched by the ladder operators defining your particle and hole excitations. And that gives you a way to build up the Lanchas spaces from the moments such that you get these A and B Lanchas coefficients. And then from those, there's a well-known representation of the Green's function called the continued fraction representation from the Lanchas coefficients that you can use to build up your Green's functions. So we take our moments and we use them to, through the cumulants, and an expression I'll show later in the next slide, you can build up, so we've got moments of the Hamiltonian, and you can build up a relation between the cumulants and the Lanchas coefficients from those moments. And then use those, so basically you're using your moments to build up the coefficients of the Lanchas, the Lanchas coefficients. And then from those A's and B's, you build up the continued fraction representation of the Green's function. But it all goes back to a measurement of these, it all goes back to a measurement of these expectation values of this operator that I'm going to call this the sandwiched moment, or the sandwiched moment. Building these, so where you take the ground state, or some representation of the ground state, and then you apply a ladder operator to it. If you did that on paper and expanded it out, you would see that, okay, you're going to end up with some, in general, kind of linear combination of terms again, some normalized linear combination of terms. And that is precisely where we're going to use the Green's function code to generate linear combinations. So from those, we can generate our basically our left and right vectors of this, and then by taking the expectation of the Hamiltonian moment with respect to that, we get basically our expectations of the sandwiched moment, and those expectations are what we use to build the cumulants, which can be used to build the Lanchas coefficients, and then the Green's function ultimately. So, for example, just taking the Hubbard dimer as an example, so you can write the ground state like this. So we have the same kind of convention as we use in chemistry. And now if you apply the ladder operator to this, you get something like, you get this kind of normalized linear combination. And we can use our Gibbons rotation code to prepare those states. And then we have those states on a circuit, and then we apply the Hamiltonian moments, just like we did before for the energy. We can apply, oops, sorry. Just like you did with for the energy. But now our state prep is this this ladder operated ground state, you can think, made again by Gibbons rotations. And now if to that we then apply the moments and we measure those moments, this expectation value then is the expectation value of this operator then in turn. And from those expectation values, we build up our cumulants and our adjust coefficients. And that gives us a Green's function. And that Green's function we measured on the actual H11 trapped ion device. And what we can see here is that the heights of this, so this is the spectral function, which is just the trace of the imaginary of the Green's function, which is that's basically the density of states for that system. And you can see here that so the black line is classical exact diagonalization, and the dots are from the hardware or the emulator. And the excitation energies themselves are very, very well defined. So there's no error mitigation there at all. It's just straightforward. Granted, the circuits are quite small because it's only the Hubbard dimer, but it's kind of nice to see that even without any error mitigation, you get very, very good excitation energies. The weights are a little small, but that's coming from the noise on the circuit, because when you look at the expression here, oops, sorry. When you look at the expression here for the A's and B's, noise, kind of the type of noise that we saw on the device affected the B coefficient more, and the B is related to the normalization of your states. So there's kind of, you can kind of intuit there that, because if there's an error in the normalization of the states, that's going to result in an error in the weight of the spectral function. So we were seeing errors like that, but the excitation energies themselves are quite good. And you can use this in DMFT as well. So here we use that Green's function calculator as the inside the impurity solver block of the DMFT routine. I'm not sure if people are familiar with dynamical mean field theory here, but basically what you have is you want to generate you want to basically represent the Green's function of the full system by an impurity model. So what you do is you focus on one small part of your system that you're interested in. You define that you use an Anderson impurity model to define that, such that the other modes that you're not interested in are represented by a bath, and then you have one body excitations between the impurity and the bath. And that works because I think I have this on a supplementary slide actually. Oh. That one. Yeah, there we go. So you have this these one body excitations between an impurity and a bath, and those parameters for the impurity bath interactions define something called a hybridization function, from which you can get your Green's function and your self energy for the impurity model. And then you want to fit that impurity Green's function to a representation of your Green's function you're basically looking through the hybridization function. You're trying to fit the impurity Green's function you have to the corresponding block of the Green's function of the full system, and that gives you a way to basically solve for the dynamical properties of that embedded system without looking at the Green's function of the entire system, basically. So it's kind of a quantum embedding method that gives you dynamical correlation. And we can so that whole embedding method, the important part of it is the Green's function calculator for the impurity part. And the Green's function method I mentioned earlier involving the subspace routine was used as the solver for this DMFT model, where we looked at a varying number of baths, and even so this is hardware itself. This is the emulator, again getting very, very good agreement with the exact result. This is for 2 baths, and then this is for 3 baths, and the even the presence of noise here, you're kind of getting a reasonable representation of the low-lying excitations energy anyway. And in this case, this was too expensive to run on hardware, so we just did the ideal state vector simulation. And the difference there is not from any quantum noise, but it's actually from the truncation of the dimensionality of the Krylov space. In other words, the fact that we would need to go to higher Krylov dimensions or correspondingly higher moments of the Hamiltonian to get closer and closer to this classical exact result. But again, for the low-lying excitations, it's kind of a reasonable approximation. So basically, we have a Green's function solver using a subspace method and using the chemical state preparation that works for the Hubbard model and for dynamical mean field theory. And at the moment, we're implementing ways to kind of make this more general, to apply it to chemistry Hamiltonians, and to possibly do quantum versions of something like DFT plus DMFT, where you can start looking at these techniques for actual real materials and molecules, etc. So that's in the pipeline at the moment. And that, I believe. Oh yeah, then just one more slide. Just to, so here we're showing the so this is so the DMFT is an iterative procedure where every iteration you're looking at basically the error in the Green's function, and when it converts, in order for it to converge, you want to see that error going down in every iteration. And this is exactly what we're seeing here, which is nice to see because these are actually noisy results. And so this is from the emulator with the noise model calibrated to the hardware, and even with noise, you're seeing very reasonable kind of convergence of the Green's function to the accurate thing. So even in the presence of some noise, we can get reasonable Green's functions out of this. So that's it. As I said, so those were the combination of the chemical ansatz or state preparation with subspace methods. We can use it for energies, we can use it for dynamic response functions, and we can handle tricky things like strong correlation and do interesting things like spectral functions and stuff like that. So yeah, thanks very much for listening, everyone. Thank you.
Are there more questions from the audience?
I have some quick questions.
Please,
For
yeah, please.
the QCM4 side, so that state preparation, that's not like you've classically found the combination of determinants you want, you're not variationally changing those.
That's right. So yeah, that's a good point. I did mention the given rotation stuff can be used for variationally find the coefficients. You can also use it, and we've implemented two ways to do it. You can just plug in a fixed set of coefficients that won't be variational parameters, but that will represent, that's the state we want, for example. So you can think of it as a way of we already have this in a sense, which is the Hartree-Fock. So the Hartree-Fock state is that's a state with a fixed coefficient in a sense, right? We're doing the same thing, but now more than Hartree-Fock. So you have fixed coefficients for a state that is better than Hartree-Fock.
Yeah.
Not as good as the ground state, but it's better than Hartree-Fock and still cheap. And actually, sorry, did I answer your question or?
Yeah, so you're by using higher movements, that's how you get a better estimate of ground state energy.
For the energy.
Yeah.
For the energy, yes. To get your question is leading into a hard part of this method, which is that okay, so we have an input state, we have moments, and then we get an energy. And as I said, that energy is better than the energy represented by this. But then you'll ask, okay, so what's the state represented by this? That's hard. I don't know how to do that. At the moment, I don't know how to. So what I mean is, so you have a bunch of moments, and those have generated an approximation of the energy that depend on connected moments or cumulants. And now the question is, how do we use these to build back the precise state represented by that energy? I don't know how to do that. It's a difficult problem. Yeah.
Is that energy,
You may.
is that energy variational?
No. It would be variational if so we're truncating the moments to order 4. In general, so these moments are used to span a Krylov space, right? And you want and so that Krylov space is you're basically using that to expand an approximation to the ground state in. So if the dimensionality of that Krylov space matched the dimensionality of your actual ground state, you could represent the ground state exactly in that Krylov space. But now you truncate that Krylov space, and you're going to have some less than exact approximation to the ground state. So you can think of it as choosing some dimensionality of your Krylov space to expand in. But that chosen dimensionality will be a function of your moments, such that if the dimension of the Krylov space you want to expand in is d, the maximum moment you need for that dimension is 2d minus 1. So if you have dimension, if you want just 2 dimensions of your Krylov space, so if you want 2 dimensions of your Krylov space, you need a third moment, right? If you have, I think in this one, for this Green's function, we had 8, I believe, for the 2 of these. Dimension Krylov space, which would be the 15th moment would be the highest one in that case. So why I'm saying this is because when you get the approximation of the energy that involves up to the maximum moment for that Krylov space, then that energy is variational. But because we're truncating to the 4th, unless your system was small enough such that the 4th already saturated it, you're truncating it to the 4th, it's no longer variational. But it often is a good approximation to the energy in that case. But yeah, it's a good question.
How quickly does that converge? As in, if you said, well, I want it to be variational, so therefore I can only measure up to 4th moment, so therefore I need to take my much smaller Krylov space. Is that
so?
Or, why are you going to these really big ones? Yes.
So if this, so really what we're doing is we're solving a projection of the Schrodinger equation on some subspace. So that means that you have these. So this is a matrix, and this is a matrix, and this is an overlap matrix. So if the matrix elements of those matrices were measured exactly, so if there was no quantum noise, or the quantum noise was small enough that the noise was small enough that this problem was not ill-conditioned. For example, the noise didn't lead to non-positive semi-definite S. When all those conditions are satisfied, actually the accuracy of the energy scales exponentially with the Krylov dimension. So once everything is clean, the Krylov dimension converges exponentially fast with respect to the dimension. The problem is the effect of noise. Yeah.
So that's why you want to go to these bigger ones.
Bigger ones.
So it's better to have a bigger effective Krylov space than to just try and clean up your smaller vectors.
Yes, it can be, but it all goes back to how you're implementing the unitaries to generate that Krylov space. So what's more costly, generating those Krylov vectors explicitly, or measuring the moments of the Hamiltonian, and which one are you using to get to the dimension you want to get? I'd love to give a theoretical general answer, but there's so many things there that it inevitably becomes a practical question, system dependent. Yeah. This review is really, really good for those points I mentioned. I'll share the slides. I have no problem with presenting most of either, but yeah, that motor review released recently, very, very good, very, very good on all these points.
I had a question about the sparse state preparation that you talked about, even though I know it's not really about.
Sure thing.
Yeah.
No, I
You say it's linear. It can be linear scaling if you have less than like 2 to the n over n scaling in the number of non-zero elements. So is that a linear scaling in depth?
It's a linear scaling in depth. Yes, in depth.
And does it include ancilla qubits?
Yes. So it's yes. So it will be. It comes down to the fact that wherever the controls are used in it, they go back to they rely on another recently generated algorithm which shows that multi-controls can be decomposed.
Like the multiplexer.
Yes,
Yeah.
the decomposition of multi-controls is linearly scaling with respect to the number of controls, the number of control qubits, and that algorithm was only found recently. So once you have algorithms decompose the multi-controls involved in those unitaries, and then so I'm trying to bring up, maybe if I share another.
window.
So, yeah, I was just wondering if the number of ancillas you need actually scales badly.
No,
Okay.
so the scaling, the entire scaling of it, goes down to the fact that there are, so if here, magnitude S is the number of basis states. So these while loops that they're talking about are looping over. So you're going to give it some list of basis states at the beginning, and then it's going to loop over all of those basis states and see kind of not unlike, but there's significant differences as well. How I was saying earlier, where you apply sequences depending on the order of their on the given list of determinants. Here you have a while loop, again going over all of the determinants, and each one it's seeing where to apply x's and control rotations, so in order to get the desired linear combination. The point is that the number of those while loops, so each while loop puts one of these controlled unitaries on it. So the algorithm is very smart in that you don't ever have, believe it or not, these multi-qubit rotations. Everything you do is from controlled single qubit controlled rotations. So every iteration is going to add one of these single controlled unitaries plus some other controlled operations like C-naughts in order to make the basis state, the state vector, the desired one. But the number of those while loop iterations, which is the number of these things, is actually is logarithmic in the number of basis states. And then the number of C-naughts, and then for complicated reasons, the number of C-naughts you need is also going to be logarithmic in S, and that in turn depends on spatial multi-control algorithms that were also implemented recently. So it actually so that condition for linear scaling is satisfied for the depth and the number of gates, I believe. Actually, yeah. And just to put it super explicitly, it's kind of annoying that you have to go way down to the conclusion to actually find this criteria, but their criteria is the sparsity condition. So once this sparsity condition is satisfied, then their good scaling criteria is applicable, apparently.
Okay. Thank you.
I have some pizza.
Of course.
Oh, thank you. I'm so sorry.
Sorry.
I didn't have my
Yeah, there's a whole thing out here, so great. Thank you very much.
Thank you so much. Thanks again. I probably didn't answer your question very good.
No. I was just
But there's essentially there are advantages to measuring these things using operator averaging and stuff over evaluating.
is sort of getting an advantage from